Alright, so we've gone over the postulates of quantum mechanics. It's now time to apply them to we're going to start with applications to simple systems. Okay, so we're going to start off with the free particle, and that's the simplest possible system that you can apply quantum mechanics to. And before we do that, let's do a little math background. Let's talk about second order differential equations. DE means differential equations. A differential equation is just an equation that has derivatives in it. And your goal in a differential equation is to solve, when you solve a differential equation, you look for a function that would obey that equation. So for example, if I have, this is the common type of differential equation you will encounter, where you have some constant A times the second derivative of y with respect to x, okay, plus another constant b times the derivative of y with respect to x, so that's what y prime is, plus some constant c times y is equal to 0. So this is what's called a second order differential equation because the highest derivative is a second derivative, okay? So if the highest derivative is a second derivative, we say that's a second order differential equation. The highest derivative is 1, first derivative, then that will just be first order. Okay, so let's take a look at this one. It's a common differential equation you might encounter. Let's show that e to the sx is a solution to this. In other words, if I plug in e to the sx, if I plug in e to the sx for y, that it will obey this equation. So let's do that. So s is a constant, so I'm going to say 1 a times second derivative of e to the sx is what? What's the derivative of e to the sx with respect to x? S e to the sx, and then take the derivative of that again, that's s squared e to the sx. So this is going to be s squared e to the sx plus b times, what's the derivative of e to the sx with respect to x? S e to the sx. So, and then plus c times e to the sx equal to 0. Okay, can I factor something out here? E to the sx, e to the sx, e to the sx, I can factor that out. E to the sx times as squared plus bs plus c equal to 0. So you know it's going to be a solution if there is an s that would satisfy this, right? So when two things equal to 0, either, so if a, b is equal to 0, either a is 0, right? Or b is 0, or both are 0, right? E to the sx, since x is generic, is a variable, we can say that's not going to be equal to 0. So this must be equal to 0, this expression right here. So we say then that for e to the sx to be a solution to this differential equation, in order for e to the sx to obey this equation, then it must be true that as squared plus bs plus c is equal to 0. So what are the two allowed values of s? Quadratic formula, negative b plus or minus square root of b squared minus 4ac over 2a. So there's two possible s values, okay? Unless it's a perfect square, in which case there's only one s value. And what you'll find in that case is that x times e to the sx is also a solution, okay, if it's a perfect square. But in this case, you're going to have two possible values of x. Let's call that s1 and s2. Then the two solutions are e to the s1x and e to the s2x. Okay? So let's apply that to this problem right here, simple problem. 4 times the second derivative of y with respect to x minus y is equal to 0. What are the two possible values of e to the sx? So let's just cut to the chase here. Let's identify a, b, and c. Remember, this is of the form a y double prime plus by prime plus cy equal to 0, right? So what's our a? A is 4. What's our b? 0. What's our c? -1. So s would be equal to -0 plus or minus square root of 0 squared minus 4 times a, which is 4, and c is -1 divided by 2 times a, 2 times 4, right? And that's 1. So plus or minus square root of, what is 4 times -1? 16. Right? That's square root of 16 over 8. So plus or minus 4 over 8. So plus or minus 1/2. So e to the 1/2 x is a solution. And so is e to the -1/2 x. You have two solutions. And you plug that back into your differential equation. You plug it back in here, and here, and here. You should get 0. Okay? Now, the general solution of a second order differential equation is a linear combination of two linearly independent solutions. Okay? So this is a second order differential equation. That means the highest derivative is a second derivative, right? When we're solving it, basically what we're doing is we're integrating twice to get the function, to get back the function, right? So if you integrate twice, you get two integration constants. And so we can if let's say f1 is a solution and f2 is a solution, then you can say the general solution f is going to be c1 f1 plus c2 f2, a linear combination, provided your f1 and f2 are linearly independent. What do we mean by linearly independent? f1 cannot be equal to just some constant times f2. That's what linearly independent means, right? So like for example, sine x and cosine x, are those linearly independent? Can I write sine x as just some constant times cosine x? No, so those are linearly independent. But what about negative sine x? Sine of negative x. Is sine x and sine of negative x linearly independent? They're not independent, right? But what is sine of negative x? So sine of x, negative sine of x is just a constant times sine x. See, they're not linearly independent. So you have to find, in other words, to get the general solution of a second order differential equation, you have to find two linearly independent solutions and take a linear combination of the two. All right. So earlier, what did we say are two specific solutions, linearly independent solutions? E to the s1x. This is the same problem we had earlier, right? And so our two possible solutions are e to the 1/2 x and e to the -1/2 x. So those two are linearly independent solutions. Okay, so e to the 1/2 x and e to the -1/2 x. Each one of these, if you plug it in, it gives you the right answer, right? It satisfies the equation. The general solution would be c1 e to the 1/2 x plus c2, c1 and c2 are constant, e to the -1/2 x. That would be the general solution. Let's verify that that is in fact the general solution. What would you do? You plug that in, right? So what is y prime? c1, what's the derivative of e to the 1/2 x? e to the 1 half x plus c2 negative 1 half times e to the negative 1 half x. So that's your y prime. What's your y double prime? C1 1 half squared, right, was 1/4, e to the 1 half x, and C2 negative 1 half squared, so that's 1/4, e to the negative 1 half x. So what was our equation? Our differential equation was 4y double prime minus y, right? So 4y double prime minus y equals 4 times C1 times 1/4 e to the 1 half x plus C2 times 1/4 e to the negative 1 half x. That's your 4y double prime. Minus y, which is C1 e to the 1 half x plus C2 e to the 1 half x. Is that correct? What is, so I can factor out this 1/4, right? And cancel out the 4. And what happens? That whole thing is just equal to 0, right? And which is what we want, 4y double prime minus y. Okay? Each one of these solutions, you plug it in, it will satisfy this differential equation. The linear combination of the two also satisfies the differential equation. So this is what you would call your general solution. Okay? The general solution is a linear combination. Okay. Differential equation. Huh? This is an example of a differential equation. Equation that has derivatives. Your goal when you solve a differential equation to get the function. See, this is a differential equation. 4 times the second derivative of y with respect to x minus y equal to 0. This is an equation that has a derivative of y in it. The second derivative. So your goal in a differential equation is to solve for y, the function. If there's a derivative in your equation and you want to solve for the function, that's called a differential equation. Okay? All right. How about this one? What's the general solution for this? Okay, so let's just, this is the same type, right? A_y double prime plus b_y prime plus c_y equal to 0. So what's our A? 4. What is our B? 0. What's our C? So what are our two possible values of S? So our solutions would be e to the sx, right? S would be negative 0 again, plus or minus square root of 0 squared minus 4 times 4 times 1, 4ac over 2 times a, so 2 times 4. So that's going to be equal to this plus or minus square root of negative 16 over a. What's the square root of negative 16? 4i. Okay, so that's plus or minus 4i. I is square root of negative 1, right? Over 8, so plus or minus I over 2. So what's our general solution? Constant times e to the I x over 2, right? Plus c2 times e to the negative I x over 2. That's your general solution. Got it? All right. Boundary conditions. Boundary conditions put restrictions on the constants in the general solution of a differential equation. In other words, when you solve a differential equation, you find that there's a lot of functions that will satisfy that differential equation. Look, like in this example right here, C1 and C2 can be any constant, right? So there's a lot of different solutions that would obey that equation. Now, typically, when you set up a differential equation, it's to solve some kind of physical problem, right? And so the physical problem itself, the reality is going to impose certain conditions on your solution. Those conditions that must be satisfied are known as boundary conditions. So when you apply those boundary conditions, you'll find that not all of these, you cannot just have any C1 and C2. It will impose restrictions on what those C1s and C2s can be. So by imposing boundary conditions, you just take a subset of all the possible solutions. Okay, so this example we have right here, that's the one we just solved, right? 4y double prime plus y equals 0. Yeah. So what's our general solution? C1 e to the ix over 2 plus C2 e to the negative ix over 2. So let's remember our solution to this. Y equals C1 e to the ix over 2 plus C2 e to the negative ix over 2. Okay? What if we want y to be 0 when x equals 0? So that's an example of a boundary condition. Let's say I'm solving I have this problem. Then this is the differential equation. I need to solve that problem. And I know that if x is 0, y must be 0. So you plug it in. Okay? So when you impose your boundary condition, you're going to say y is 0 when x is 0, right? So y equals C1 e to the I x, which is 0, right? Divided by 2, plus C2 e to the negative I, and x is 0, divided by 2. What is that then? E to the 0 is 1, right? And e to the negative 0 is 1. So C1 plus C2. What are we saying then? C1 equals negative C2. The negative of each other. So if C1 is 5, then C2 is going to have to be negative 5. If C1 is 4, C2 will have to be negative 4. So in other words, if I know that y must be 0 when x is 0, I'm not allowed to use C1 equals 5 and C2 equals 6. This will obey the differential equation, but it will not satisfy my boundary conditions. So I throw out this solution. I only keep the solutions where C1 is equal to negative C2. Okay? So that's a common thing you do when you solve differential equations. Generally, you set up a differential equations to solve some kind of physical problem. And the Schrodinger equation is a second-order differential equation. And what you'll see as we go along is this is where quantization shows up in quantum mechanics. So once you solve the Schrodinger equation, when you impose boundary conditions, that's when you start to see the phenomenon of quantization of energy. Okay? All right. So we're now ready to tackle the simplest possible problem we can deal with. We're going to look at the free particle. This is a particle that's it's moving in one dimension, okay, and the potential energy is 0 everywhere. That means along the x, let's just say it's along the x-axis, that dimension. Along the x-axis, it's not experiencing any force at all, so its potential energy is constant. Okay, what's our Schrodinger equation? Time independent, do you remember? H hat psi equals E psi. Okay, and that's always going to be your first thing you're going to try to solve. You solve for stationary states by solving the time-independent Schrodinger equation. So H hat psi equals E psi. What is the Hamiltonian operator? It's kinetic energy plus potential energy, right? But what's the kinetic energy operator? Negative h bar squared over 2 times the mass times the second derivative with respect to x. Right? And potential energy operator is to 0. It's a multiplicative operator in this case. It's 0. So h hat psi then is negative h bar squared over 2m, second derivative with respect to x, operating on psi. So that's your h hat psi is equal to e psi. This is your differential equation. And let's rearrange this to something that is a little bit familiar. I'm going to move my m and my h bar squared on the right. So what do I have? Second derivative of psi with respect to x equals, I'm going to move my m over there. So it's going to be 2m times e, right? And my h bar squared, I'm going to move over there. So that's going to be over h bar squared, and it's going to be negative, right? Times psi. And this is just a constant, right? And so move everything to the left. I can rewrite second derivative of psi with respect to x plus 2me over h bar squared psi equals 0. Okay, so this is like ay double prime plus 0y prime plus cy equals 0, right? So what's your a? 1. What is your c? That constant right there, and b is 0, right? So what's the general solution to this? What's our s? S equals plus or minus 0, negative 0 plus or minus 0 squared minus 4 times a is what? C is 2me over h bar squared divided by 2. And so that's negative of plus or minus, okay, negative 8 me over h bar squared. Now, mass is positive, energy is positive, h bar squared is positive, so this expression here is positive. So I have a square root of a negative number then, right? So I can factor out square root of negative 1, so that's going to be plus or minus I times square root of 8me over h bar. And I forgot, I have that divided by 2 down here. Okay, I'm going to move my 2 inside, okay? So what happens if I move my 2 inside my square root sign? It becomes a 4, right? So plus or minus I square root of 8me over 4 over h bar. So that's equal to plus or minus I square root of 2me over h bar. So those are my 2 possible s values. Positive I squared root of 2me over h bar and negative I times square root of 2me over h bar. So what is the general solution to the Schrodinger equation for a free particle? We say psi as a function of x is equal to some constant c1 e to the I kx, where k is this one, right? I'm getting lazy, so I'm just going to call this one k. K is square root of 2me over h bar plus c2 e to the negative I kx. Okay? And so that is your general solution to a Schrodinger equation for a free particle. And since it's a free particle, there's no restrictions on it. That's the solution. Okay. So that's just a review. Psi is some constant A, e to the ikx, plus another constant B times e to the negative ikx. What did we say K was? Square root of 2me over h bar. Okay? All right. What are the allowed energies? How is the energy related to kh bar? To k. How do I solve for k? Energy. K is square root of 2me over h bar. So if I want to solve for energy, what do I have? K and h, and then you square it, right? So k h bar squared over. All right. There's no restrictions. Energy can be anything, right? K can be, yeah, there's no restrictions. It's a free particle. No quantization. Okay? Now, what if, for some reason, we want A to be 0? Okay? And let's say, and we're going to give an interpretation to that. What if A happens to be 0? What would happen if, for some reason, for physical reasons, we have to set A equal to 0? What does that mean? Well, if A is 0, what happens here? That drops out, right? What is psi star psi squared? What's psi squared then? It's going to be b e to the negative ikx star times b e to the negative ikx, right? Psi star psi. What is b star times b? Absolute value of b squared. And what is e to the negative ix times e to the ix? That's just e to the 0, right? So psi squared is just going to be absolute value of b squared. What does that mean? Equally probable, finding it everywhere. It has no preference. You'll have absolutely no idea where the particle is going to be. Okay? Note that, like I said, psi, hold on. Yeah. Psi, you'll notice here, is not normalizable because what happens when you take psi squared over all space? Integral of b squared e to the 0 dx from negative infinity to infinity. What is that? Absolute value of b squared. What's integral of dx? It's just x, right? Evaluated from negative infinity to infinity. That's infinity minus negative infinity. Yeah. It's not normalizable. Okay? Your psi here is not normalizable. All you know is psi is uniform throughout. And that's because that's typically what happens when you have what's called an unbound system. Your free particle has no boundaries. And strictly speaking, when you have, there's really no such thing. Everything in nature has a boundary somehow, right? So this is really an idealization. So you don't see your psi here being normalizable unless you decide that I want it confined to this region in space. Okay. So if there's no restriction on where the particle can be, you have what's called an unbound system. So this is one exception where you cannot normalize your function. Okay? But one thing you'll notice about this is that linear momentum is well defined. How do you determine the linear momentum? How do you determine if this is a well-defined linear momentum? Then psi must be an eigenfunction of linear momentum operator. What's your momentum operator? H bar over I derivative with respect to x, right? So let's apply p hat on psi. What do you get? h bar over I d by dx. And what was I psi? It's just b e to the negative ikx, right? And what does that give you? H bar over I times b. What's derivative of e to the negative ikx? Negative ik times e to the negative ikx. And this one, that's just psi, right? So that's psi. And I and negative I cancels out. So that's negative h bar k h psi. So p hat psi gives you back a constant times psi. So what is this? That's a constant. So that's an eigenvalue, right? So we say psi in this case is an eigenfunction of the linear momentum operator. So it has a well-defined momentum. What's the momentum? The momentum is negative h bar k. What does negative h bar k now? You know k is a positive number, right? So the momentum is negative. That means we're talking about a particle that's moving to the negative direction. Or if you say the left is the negative direction, the right is positive direction, we're talking about a particle that's moving to the left. Okay, well defined. So this particular wave function, just this part, describes a particle that's moving to the left. Very well, and with the magnitude of the angle of the linear momentum equal to h bar k, and it's negative because it's moving to the left. Very well defined. You know exactly what the linear momentum is, but what's the consequence of knowing exactly what the linear momentum is? You have no idea where it is. Okay? So here's your momentum, negative h bar k. Remember, h bar is h over 2 pi. Now let's try to relate this to energy. Remember what did we say energy was? It's just h bar k squared over 2m. And that's just equal to p squared over 2m in this case, right? h bar k squared is the same thing as negative h bar k squared, right? So your energy is also well defined, right? It's equal to h bar k squared over 2m, which is p squared over 2m. This is formula from classical mechanics, right? Kinetic. The only energy the particle has is kinetic energy, 1/2 mv squared. It's the same thing as p squared over 2m. Right? So energy is well defined. Momentum is well defined. You have no idea where the particle is. All right. What if b is 0? Then probability density is uniform everywhere, right? Absolute value of a squared, constant, right? And your momentum is going to be positive h bar k. Your particles are moving to the right. Okay? And just like before, you have your psi here is not normalizable. Okay? So this is a good thing to remember. E to the ikx and e to the negative ikx, those are eigenfunctions of the momentum operator. Okay? So what is the momentum for this one? Positive h bar k, and the momentum for this one is negative h bar k. So what are we saying here then? In general, you'd have no idea what the momentum is. Some particles could be moving. There's a probability the particle could be moving to the left, and there's a probability that the particle is moving to the right, right? So a squared and b squared, if you compare those two, that will give you an indication of the likelihood that it's moving to the left and to the right. Remember, the probability that the momentum is negative h bar k is directly proportional to absolute value of b squared, right? In fact, if you want to normalize with respect to momentum, you're going to say that a squared plus absolute value of b squared must be equal to 1. So in a way, you can normalize this function in terms of momentum. The total probability, there's the magnitude of the momentum is well defined. Okay, so magnitude of the momentum is h bar k. Okay, but in general, there's a likelihood that the particle might be moving to the left, and there's some probability it might be moving to the right. Those probabilities are proportional to the coefficients of these eigenfunctions of the momentum operator. Now, what if A equals B? What would happen? If A equals B, I can factor it out, right? So A times e to the ikx plus e to the negative ikx. You've seen this before lots of times already in the Euler formula. What is this? Cosine kx plus I sine kx, right? And this one right here is cosine kx minus I sine kx. So if you add the two, what do you get? Sine cancels out. That's 2 cosine kx. So psi will be 2 times A times cosine kx. Right? So you're saying here, okay, A and B, that means A squared and B squared are equal, right? There's an equal chance that the momentum is going to be h bar k and negative h bar k. 50-50. 50% chance that the particle is moving to the left, 50% chance the particle is moving to the right. Okay, so your momentum is not well defined anymore. Okay, you know the magnitude is h bar k, but you don't know the direction. The average linear momentum is, in fact, you can show that to be equal to 0. How do you show the average linear momentum? The expectation value. And this is px, since we're doing the x-axis. It's integral of psi star px hat psi d tau, right? Expectation value of any property is calculated that way. So integral of psi star, and px is, what's that operator? H bar over I, derivative with respect to x operating on psi, dx from negative infinity to infinity. Okay? But what is h bar of I d by dx? What's the derivative? What is psi? Cosine, right? Cosine. Okay. Psi star is cosine kx, 2a, right? Star times h bar over I. What's the derivative of 2a cosine kx? Negative 2a k sine kx dx from negative infinity to infinity. Factor out all the constants you have. Right, what do you have? Negative 4 absolute value of a squared k h bar over I, right? Factoring out all the constants. Cosine kx star, and cosine kx will just be star and kx. Cosine of a real number is also a real number, so I don't have to put a star. Right? So cosine kx sine kx dx from negative infinity to infinity. What is this? This is an odd function between symmetric limits. This is just going to be 0, right? Right? If this is an even function times an odd function, this whole thing is an odd function. Right? Integral of an odd function over symmetric limits is just equal to 0. Okay, let me see if I can show you that visually. Let's plot, okay, sine x. Let's just do sine x and cosine x, right? So cosine x times sine x. So going to be y equals cosine sine x times cosine x. That's what we're integrating, right? Y is a function of x. And so let's just say x from, let's say, negative 2 pi, oops, to negative 1.99 times pi, all the way to 2 times pi. Right? So let's plot that. Insert graph, xy plot. We're going to plot versus x and y of x. There's your function right there. Sine x times cosine x. Right? So look at this one right here. It's an odd function. It's an odd function, right? So if I have a number here, go to the origin, go to the other side. So this area cancels this area. This area. I'm sorry. All right. So this area cancels that area, right? This area cancels that area. This area is positive, this area is negative. They cancel each other out. So as long as you're looking at symmetric limits, the integral of an odd function over symmetric limits is 0. In fact, let's verify that. Let's integrate y of x dx from, let's say, negative 1 to 1. Here. Okay. Let's go from negative 5 to 5. Here. Yeah, you want to do it analytically? Sure. Integral of sine x times cosine x dx. Alright. It's 1/2 of sine x squared. Okay. And so you have a value of that at one end and a value of that on the other end. Sine of x is equal to sine of negative x, right? If you square those two values and you subtract, you get 0. So when you integrate an odd function over symmetric limits, then you get 0. All right, so going back, if this is 0, then what we're saying then, your average linear momentum is 0. Why is that? Well, what's the probability that P is equal to h bar k? It's going to be what? Here, let's take a look at this one. What we're saying here is this. Okay? The probability that momentum is equal to negative h bar k is absolute value of b squared, directly proportional to, right? And the probability that it's going to be plus h bar k is directly proportional to absolute value of a squared, right? But if a and b are the same, equal probability. So what's the average momentum? 50% chance that it's h bar k, right? Plus a 50% chance that it is negative h bar k. So it's going to be 0. Okay, the expectation value of the momentum is 0. So in other words, We can normalize this. What should A and B be in this case? Since A and B are going to be the same, we're going to say this is 1 over square root of 2 e to the ikx plus 1 over square root of 2 e to the negative ikx. Okay? We're going to say that a squared over a squared plus b squared must be equal to 1/2. Okay? And if that's the case, and then a squared plus b squared is 1, right? So a squared itself is 1 over square root of 2. So if you square this, you get 1/2. And you square this, you get 50/50. Now, this could be minus. Doesn't have to be plus. All we want, what we just need to know is that the absolute value of A must be equal to absolute value of B. Okay? Oh, but we are insisting that they are equal. But another, if A is equal to negative B, you have pretty much come to a similar conclusion. All right. So normalization, like I said, in terms of momentum, is the absolute value of A would be square root of 1. All right. So let's take a look at an example. Let's say we apply this to an ideal gas molecule, a lone molecule, all alone by itself in the universe. So and let's take the typical case where if you have a sample of an ideal gas, you'll learn that the average kinetic energy of the molecule is 3/2 kT. Okay, so that's 3/2 times K. K is Avogadro's number, Boltzmann's constant. So that's the gas constant, 8.314 joules per mole per Kelvin, divided by Avogadro's number, which is 6.02 times 10 to the 23rd per mole. Okay. And our temperature is, let's just say, 298 room temperature. So what would be our average energy of our molecule? So let's do this on MathCAD. Okay. So our kinetic energy would be E equals 3/2 times Boltzmann's constant times temperature. Okay, so we have to tell it what Boltzmann's constant is. K equals, what is it, 8.314 joule per Kelvin per mole. And that's divided by Avogadro's number, 6.022 times 10 to the 23rd. Let's just call that n sub A. And Avogadro's number is n sub A equals 6.022 times 10 to the 23rd per mole. Okay, so what's the value of Boltzmann's constant? K equals, oops, it's not 0, but it's less than 10 to the negative 15, so it's showing it at 0. Let's set our format so that our zero tolerance is less than 10 to the negative 15. So let's make that 10 to the negative 300. So that's your Boltzmann's constant. 1.38 times 10 to the negative 23, and you can put that in terms of joules. That's joules per Kelvin. Okay? What's our temperature? Let's define our temperature. Notice it's not complaining about that T, because T is one of MathCAD's predefined variables, so we have to override that definition with our temperature, which is 298 Kelvin. Okay, so our energy is equal to 6.171 times 10 to the negative 21 joules. Okay, what's the mass of our helium atom? Let's say our helium atom is our ideal gas atom. Mass of helium is 4.00 grams per mole, right? Now let's express that in kilograms per atom. So divided by Avogadro's number, 6.02 times 10 to the 23rd per mole. That would get rid of gram. Gets rid of per mole, right? So that's per gram. That's grams. And how many kilograms in a mole? Actually, I don't have to do that conversion anymore because it will tell me the answer in kilograms. Okay. Or if you want, you can manually show the conversion here. You can say times 10 to the negative 10 to the third, 10 to the negative third kilogram per gram. Same thing. You don't have to put that conversion factor in because MathCAD knows how to adjust your units. Okay, so that's your mass. What's our K? Square root of 2 times the mass times the energy divided by h bar. How did I figure that one? What did we say energy was? Energy is h bar K squared over 2m, right? So 2m times E, square root of 2me is equal to h bar K, right? That's your momentum. And K is just square root of 2me over h bar. So let's define h bar. It doesn't know what h bar is. So h is 6.626 times 10 to the negative 34 joule seconds. And what is h bar? H over 2 times pi, right? 2 times pi. So what's our K? That's our K. 8.856 times 10 to the 10 per meter. Okay? So what is our psi? Psi of x equals okay, our helium atom is moving to the right. So it's just E to the 1I, that's your I, times K times X. Okay? And your momentum is how much? It's just H bar times K, right? So momentum is 9.054 times 10 to the negative 24 kilogram meters per second. What's our de Broglie wavelength? Remember the formula for de Broglie wavelength? H over P. So de Broglie wavelength is 7.3 times 10 to the negative 11. Okay? Yeah. Scroll up, yeah. Energy 6.1 times 10 to the negative 21 joules.
The mass is 4 times GM.
GM is grams in MathCAD. But it cancels anyway. G is acceleration due to gravity in MathCAD. Okay. But if you want to use G, you can redefine G equals GM. Okay. That was your question? Okay. So now let's plot our psi. What would our psi look like?
On the right side is equal to h over I.
Because psi is e to the ikx because it's moving to the right.
The constant y is equal to the constant.
Oh, we just set it to 1, so the probability of the momentum moving to the right is 1. A squared is 1. Okay. We're going to say psi equals a e to the ikx. And we're going to normalize with respect to momentum, so we're just going to say absolute value of a squared is 1. remember when we did this earlier, okay, a is 1 over square root of 2, b is 1 over square root of 2 because you want absolute value of a squared and absolute value of b squared to be equal to 1. But since b is 0, it's moving to the right, a is just going to be 1. A squared is going to be 1. A can be negative 1 if you want, or any complex number with an absolute value equal to 1. All right, so what do we have now? Time to go? Okay, we're going to finish this next time. Actually, I'm going to finish this when you leave. So I'll just complete the movie, the video, and I'll post it on YouTube, okay? Or we'll just finish it next time.